So welcome everybody to this Thermal Transport Cafe. It's my great pleasure to welcome Dr. Arthur Oliveira. So Dr. Oliveira is an assistant professor at São Carlos School of Engineering in the University of São Paulo. He's been there for about 3 years. He did his bachelor's mechanical engineering and his PhD in mechanical engineering, both at the University of Campinas in Brazil. Then after that, he spent some time in industry, working as a product engineer at Marelli Automotive Systems, working on heated fuel rail used in IC engines. And then he was doing some postdoctoral work in University of Lorraine in France. Then he started his faculty position here. So today he'll be talking about jet and spray quenching, and I'll leave the floor to him. And we're very excited to hear his recent research. So the floor is yours, Arthur. Thanks.
Okay, Matt, thank you again for the invite, for the introduction. I'm very glad to be here to present what I've done during my part of my postdoc there in France at the University of Lorraine, and what we are doing now here at the University of São Paulo with our project in the LETeF laboratory of thermal engineering in fluid systems at the São Carlos School of Engineering. So thank you everybody for being here. So Matt just presented my background. So my last postdoc here is part of what I want to present here in this topic about the tests near industrial condition done at IRT M2P in Metz in France, together with the laboratory from the University of Lorraine, focused on applied and theoretic mechanics and energies. And as I said, what we are doing now regarding droplet impact heat transfer at the University of São Paulo, here in São Carlos City. And I'm highlighting São Carlos City because normally people can think of São Paulo City for the university. But, when you think of Brazil, you have here the state of São Paulo. And when you think of Brazil, normally you think of beach and soccer and very good weather. But sorry, São Carlos, you don't have this because we are quite far from the beach. So you have to go to Santos. If you want to have good soccer and good beach, that's a very good point to go, especially about the soccer team. But if you want to come to São Carlos, it's not far from good city, good barbecue, as I said, good beach, good nature, good beer, and good food, good coffee. So if you come to São Carlos, I'll be very glad to welcome here and show you the places. So it was just this brief introduction here, this marketing moment for the place. So let's go to the talk. I'm going to present the motivations of the research we have been carrying on here in São Carlos. I'm going to talk about this near industrial conditions tests regarding quenching. So this was done, as I said, in France during my postdoctoral fellowship there with Michel Gradec, David Maréchal, Michel from the University of Lorraine, David from IRT M2P. And these results that I'm going to show here counted with the collaboration of Didier Lorionec from Nova Asco, before it was Asco Metal, and Antoine Avrid, he was a PhD student there at Atlanta, now he's in CEA. And because of this industrial background that I have, I try to link in my research the fundamentals and the applications for the research involving quenching. So here in São Carlos, I'm going to show some very recent results that we published regarding droplet impact heat transfer. And the idea is go from single droplets to spray and present you a new model that we developed. So here are the students involved in the project, Carlos, Álvaro, and João Marcelo. And that counted also with the collaboration of Dr. Kita from King's College London, who also gave a talk here at TTC a few years ago in a similar subject. So we had a lot to collaborate together here. So the quenching, for those who are not much familiar, we are talking about the rapid cooling of a metal and alloy, where we intend to tune the properties of this alloy after the process regarding, especially, for example, hardness and mechanical resistance. So we have this cooling diagram, for example, for this steel, where we have temperature over time. So for instance, if I want to form martensite, I have to cool down the part very quickly in the first seconds, for example, to form martensite at the end of cooling process. If I slow down, I may form some bainite, some pearlite, ferrite, and they have lower hardness comparing to martensite. So when we are cooling down the part to form martensite, that can be very challenging because we are talking about very high heat transfer rates. And that can lead to uneven cooling. So we are talking about stresses and deformations of the final part. And when it's regarding large pieces, it's very, let's say, easy to form martensite near the surface of the part. But in the core of the part, because of heat diffusion, the cooling process is much slower. So there you can form other phases instead of martensite. And to show you some examples, there is this pictures by Mackenzie, where he shows the effects of the uneven cooling over the surface. And we can see strong deformations of the parts here. So it's very important to design your spray system, your quenching system, to have a even and then a final part appropriate for your application. And for large pieces, there is this simulation, for example, by Liassam and colleagues, where we can see the martensite formation. It's very stable, very easy to form near the surface, but in the core, it's not that easy. So that's what motivates a lot of research on quenching process in general in the literature. We have a lot of studies regarding plate cooling with jet impingement and also bar cooling processes, also with jet impingement, water jet impingement. The thing is, many of these studies involve small samples. They start at relatively low temperatures, depending on the application. And most of them are also testing only one, maybe two nozzles. So in fact, in the industrial case, you normally have several nozzles working together. I have to highlight here the work by Czapkowski and colleagues from Brunner University, where they used 32 to 48 nozzles in a very large piece. So this study here is indeed very close to industrial case, but we can see it lacks in the literature, this kind of data. So that was the motivation a few years ago, even before I did my postdoc there at IRT M2P, together with some industrial partners and the LEMTA, the laboratory at the University of Lorraine. The IRT M2P is the Institute for Research on Materials, Metallurgy, and Processes. They built this quenching pilot where they could evaluate the cooling process of large pieces near industrial conditions. So they have a furnace, they have a furnace here, they have the water line, the compressed air to pressurize the water line, and where the cooling process takes place here at the cooling chamber, inside the cooling chamber. So I'm showing you this picture because you can have an idea of the size of the equipment. So this must be a quite big experimental bench, but here you may have more details with this schematic drawing. You have here the furnace, you have the bar cooling here, the water line, the water is pressurized by the compressed air. So you control pressure and temperature of the water aspersion over the part. In this case, I'm gonna show the results for a steel bar. So it's a 80 millimeters diameter bar and 1 meter long, approximately. And here you can have the details of the instrumentation. As you can see, we have 15 thermocouples. They are quite large. And this creates a thermal inertial effect from the thermocouple that I'm going to show very quickly how we not solved, but improved this, the solutions regarding this problem. And the thermocouples are located very, very close to the surface, and they have a regular spacing. So that allows us to have a characterization of the heat transfer process along the bar axis. And here are some characteristics of the systems. The jet ring I'm talking about, I'm going to show you an image soon. We are talking about 120 holes in the water jet ring impinging the bar. They have a small diameter. The initial temperature of the part is quite high. It can be higher in the industrial case, but it's above the austenitizing temperature. So that's enough for the quantification of the cooling process. And doing tests near industrial conditions is very challenging because you have very harsh conditions. So it's not easy to do many tests, not easy and not cheap. So after several tests, we could process and discuss well details, for example, 3 cases where we evaluated the water flow rate effect here. And for you to have an information, the jet's Reynolds number is quite high. For a free jet, this is a very high number here, as I'm going to discuss that later too. Better than showing this image is to show a video. So this video is of the setup at IRT M2P in Mass, and I'm going to run it. I tested before with Matt if you could hear the sound of that video, but you couldn't. So it's quite noisy of all the equipment moving together. But here you have the water jet ring system that I told you. You can see the hose here, the furnace, the bar leaving the furnace, and this box here, it's where you have the data acquisition system for the thermocouples. We can see the thermocouples here over the part. And so they are crossing the bar. So they are measuring the other side of the piece, okay? So it starts rolling. You start the water injection, you close everything. And until the flow is stabilized, we have to wait. So it's stabilizing the flow here before starting sweeping the bar. It's going to start soon. And you can see that during this process, we start the temperature measurement. So we are acquiring the temperature measured by the thermocouples during this cooling process. We have to remind that in an industrial process, actually, you have several rings and the bar passes inside these rings. So to simulate these many rings, after finishing sweeping the bar, the ring comes back to the start position and starts sweeping again. And it does that several times. It lasts about 2 minutes, the experiment, and it goes back and forth, and we are acquiring the temperature. So to quantify the results, it's not only the temperature measurements that matters. We want to quantify the dissipated heat, the heat flux as a boundary condition for this bar. So here we have, we consider constant properties, axisymmetric problem for cylindrical coordinates. After a few simulations, we realized that we could neglect the axial heat transfer, heat conduction in this process to quantify the heat flux. So we have a 1D transient problem that can be solved, for example, using Laplace transform. And I'm not going to go into the details of the math, it's just to show the procedure. But we have the solution in the Laplace's place as a convolution. We solve the inverse Laplace transform using an algorithm. You can use anyone's, Steph, as for example. We used Valsa and Brunswick because it's very stable and easy to implement. And as we have discrete data for temperature, we can discretize this equation considering constant heat flux per time step. So now we have a discrete form for the solution of the heat equation. And the thing is, we have the temperature measurements, we have the thermal impedance that we can calculate with the equations that I showed, knowing the material properties, geometry, boundary conditions, and thermocouple position, but we want to estimate the boundary heat flux. And that's the ill-posed problem. So we need the regularization here. There are several methods in the literature. We used Beck's function specification method for information, and that gives us a pseudo-analytical solution for the heat conduction problem. And that advantage of using a pseudo-analytical solution is that you have a very fast computation of the data, and you have a quite good accuracy to compare the results. The thing is, as we are measuring the temperature, the thermocouple we are using can have a major influence on the heat flux estimation. And the thing is that most of the studies regarding quenching, people know there is this effect from the thermocouple, but there is not much of a correction of this thermocouple signal. So a few years ago, we made a very simple model, a very simple method to correct the thermocouple signal, where we consider energy balance here on the thermocouple tip. And we can model the thermocouple response very easily, considering response time given by the thermocouple capacitance and the contact resistance here with the part. And there is a heat loss parameter to consider as well. And if we do the simulation of the thermocouple response time, that's something everybody knows, it's not new. If I have a heat flux, a prescribed heat flux in my simulation that I want to estimate, so this is my reference, depending on the thermocouple response time, I'm going to have different temperature profile responses for sure. So the black line, for example, regards the perfect thermocouple, no response time. And as the response time increases, the thermal response is damped. As we can see, we can lose the fast transients of the processes. So if I use these thermocouple responses in my inverse method that I showed you, I'm going to have very bad estimates for the boundary heat flux. So we need to use large thermocouples in the industrial condition, because if we use very small thermocouples, wire solder thermocouples, they are going to break for sure with the thermal shock. So we need to use large thermocouples. So we use this equation and we propose a least square method to estimate the parameters, where you can do a small scale experiment. And there you emulate the instrumentation you're gonna use in the large scale experiments with your slow thermocouple. Let's call it slow thermocouple. In this prototype experiment, you put a fast thermocouple together, and then you put hot water from a kettle, for example, a boiler, you can boil water and put water over your part. And then you compare the thermocouple responses. And when you do this, you have the fast thermocouple here, the thermal response, and the estimated heat flux with this fast thermocouple. When I use the slow thermocouple, for example, let's say a 1 millimeter thermocouple, so it's lower, we can see the thermal response is dumped, and the heat flux estimate is a little affected. So the method we propose, we can reconstruct the thermocouple response. So you can see it's very close to the reference, the black line, and the estimated heat flux gets much better. We also tested that for a very slow thermocouple, a 3 millimeters thermocouple, very slow response time. You can see the response time is comparable to the experiment time. And after correcting the thermocouple silo, we don't care too much about the temperature measurement, but you can see that the heat flux, the estimated heat flux, is much better with the sino reconstruction compared to the original sino estimates. So in all the quenching tests that I'm going to show you now, the results, we are using this method to correct the thermocouple silo and have a better result of the heat transfer process. So for those who are interested, we have this paper here that if you want to do this test by your own, using your own instrumentation, we made available the code for you to estimate the thermal response, the response time of the thermocouple in the heat loss parameter, and also the code to correct your thermocouple sino if you are using fast cooling or heating processes. So we made this available exactly to have better results in the literature. So the results we had from the bar, we have the 15 thermocouples here. And these results that I'm showing you already count with the thermocouple correction method that I showed you. And with this response time, we can estimate the boundary heat flux with the inverse method that I showed you over time. And we can take the peak heat flux for each ring pass. And that point, we're going to consider the maximum heat flux point. These points are going to be very useful for us for the data analysis. And if we take the derivative of the temperature, we can also have the maximum cooling rate point where the derivative is maximum in absolute values. So that also is going to help us in the processing, as well as the onset of cooling point. So, you have air convection radiation at first, but when you have the jet impacting the thermocouple location, the position, we have a sudden drop in the temperature. So this is the point that regards this onset of quenching, onset of cooling, as you prefer. So keep in mind these 3 points. We're going to use them later. So going to the results for 300 liters per minute. So we have thermocouple 1 on the left-hand side. We have thermocouple 15 on the right side. And over time, we have the temperature responses here. As we expect, the ring goes from left to right. So the temperature drop is important in the first thermocouple. Then the last thermocouple sees the same, gets the same result. And here you can see the evolution in the heat flux over time for each thermocouple. I put here only 2 thermocouples to be easier to see, because here we have the key points that I showed you before. The onset of cooling before the temperature drop, the maximum heat flux point here in the middle of the temperature drop, and the maximum cooling rate point here, somewhere in the middle between the 2 points. And I can do that for the 15 thermocouples. Okay, notice that we have this heat flux decay here. It's when you finish the pass of the ring and it gets back to the starting point. For us to compare the results, the temperature evolution, heat flux evolution over time means very little. So you normally want to put this as a boiling curve. So a heat flux over the surface temperature here. And let's say for one thermocouple, you have here the onset of cooling, maximum cooling rate point, maximum heat flux. Then you have the cooling process, the end of the first pass, the decay in the heat flux, and then this loop profile of the boiling curve. And we can do that for the 15 thermocouples, and now you can't see anything else. It's very hard to analyze anything from this mass. So what we realize is that, what if we reject unphysical data? Because as we are using an inverse method, we have unphysical results here. For instance, let's say, this is for a simulation here, heat flux over time. Let's say I want to estimate the heat flux profile here, evolution as the black line. When I apply my inverse method, there is this regularization that causes a kind of penalization, a kind of degradation in the heat flux estimate to stabilize the calculations. So this part here of the calculation, where we see this increase and then this loss of the peak, is not physical. This is a mathematical feature of the method. So I cannot, it's not a reliable result, this part of the result. So considering our simulations, our results with the bar cooling, this raise in this heat transfer, heat flux must be neglected. And the other characteristics, now considering the industrial process, our test will have the static bar and the ring is sweeping the bar. But in a real industrial process, we have several rings and the bar is passing inside the rings. So we don't have this kind of dry moment of the bar in our industrial setup. So we can try to neglect also this heat flux decay to try to represent in our experimental setup the industrial case. So when we do this in our boiling curve and we remove the unphysical data, now we have a kind of correlation between the heat flux and the surface temperature. Now we just see this kind of correlation. We can try to fit an equation here to relate the heat flux and temperature. And we can also translate that to heat transfer coefficient, depending on the industrial partner preference. And now I can try to compare these results for different water flow rates. And what we see is that from 300 liters per minute to 450, we have a small but a consistent increase in the heat transfer. But from 450 to 600, we have a kind of decrease in average, of course. We have a very minor effect, actually. But we try to understand what happened here. Why didn't it increase? So when we took a picture of the jet ring system, we first thought maybe there is a gravitational effect here, the wake of the jet after hits the bar again, but we don't see a major change in the geometry of the wake. So it's not a major effect. What we realized, we have a difference here at the nozzle. And when you compare the three conditions, we can see a kind of fog near the nozzle for 600 liters per minute. So we're starting to have some atomization here, which confirmed when we put that in the Ohnesorge diagram. We are getting closer to the atomization regime. So as we are talking about 120 nozzles, when you have the atomization, this droplet will be dragged by the air inside the systems, or even by the jet, and maybe will not even reach the wall. So that can be kind of a degradation of the heat transfer. Because here we are talking about a much larger scale compared to what we see in the laboratory. We are talking about much more nozzles, a much higher water flow rate. So maybe we kind of reach a saturation here in the heat transfer. But this is a very strong affirmation to do. So after a new test with a thermocouple in the core, because if we have very different heat transfer conditions, we should see a temperature difference in the core of the material after a while. But when we did the test, after 2 minutes of cooling, there is no major difference in the temperature measurement in the core of the part. You can see that after 500 degrees drop, there is only 2 degrees difference between the two tests for the two flow rates here. So no, there is no major effect of the water flow rate in these conditions, of course. And when we use the correlation we proposed for a real industrial test, so here we have a real industrial line, we consider the parameters to use the correlation, we consider metallurgical effects, and considering that there is a very simple equation to put in your model, we quite had a sufficient, sufficient accurate result, let's say, comparing the experiment and the model. After almost 900 degrees temperature drop, we had only 80 degrees difference between the model and the experience, the simulation, the experience. And that can be also related to nonlinear effects, because when you have phase transformations, you have latent heat of phase transformations, you have not constant physical properties. So that can play a role. So that's the first part of the talk, when I wanted to show this industrial condition, because what happens is that during this industrial background that I had, when you have a problem in the industry and you want to solve it, sometimes you need to scale down your problem to try to answer it. And that's why we need to have reliable and high quality laboratory data to apply that for industrial case. It's not new what I'm talking, but when you have a scale change in engineering, this problem can go from industrial case to pilot scale to laboratory scale. And that's very challenging when involving phase change processes. And also for a development, and I think that's one of the roles of ours in the university. You have a desired development, you see something at the laboratory scale, you try to increase the scale, and that can also be very challenging, sometimes frustrating, to not see exactly the same phenomenon as we scale up or down the problem. So that's actually the motivation of my research here at the University of São Paulo regarding quenching using sprays, because we have a lot of data in the literature regarding single droplet impact heat transfer, but that's actually too fundamental. And we also have a lot of spray cooling data in the literature, but that's very application driven. Sometimes one result for spray cooling cannot be easily extrapolated to another condition, you know. So maybe testing multiple droplet impact is a way to link the two problems. So that's the objective of our research here at the Laboratory of Thermal Engineering Fluids. So this is the laboratory where I'm working with, and the group that I lead inside the laboratory is the group GOTAS, Group of Optical Techniques, Application in Sprays. For those who speak Portuguese, Spanish, they understand GOTAS is droplet in Latin language. So that's what we are doing here, using optical techniques to evaluate and quantify droplet impact dynamics and heat transfer. So we use shadow graph, infrared thermography, and total internal reflection as techniques, as well as LETeF to measure the liquid temperature. The videos that I'm showing are example of results that we had here in the lab, but to focus on only one result, I'm going to show results we recently had and published regarding shadow graph and infrared thermography for droplet impact heat transfer over metallic sheet. So we have here the stainless steel plate, which is heated by Joule effect. We characterize the droplet impact by shadow graph, and the infrared camera measures the surface temperature. And here are some characteristics of the tests. We have water as test fluid. We have a fixed droplet size of 2 millimeters. We vary the impact velocity by changing the droplet release height. And the plate was a 0.5 millimeters stainless steel plate. And as it's very new for us here in the group. The test started by the end of 2023. So it has almost 2 years that we started having the results. So we started with relatively low temperatures. Now we are starting experimental campaign to go to much higher temperatures. But the raw results we have from these experiments are the shadow graph images that you can see here and the infrared images. And you can see some characteristics of the image acquisition here. So as before, we need to develop an inverse method here to quantify the heat flux field over time for our droplet impact process. So now we have a 3D transient problem, and we use Laplace and Fourier transform to have an ordinary differential equation. Using Laplace transform, you have the solution in the Laplace space. And also we use an algorithm, the same algorithm, to invert the Laplace function. And we discretize that by considering constant heat flux profile per time step. The difference now is that we are estimating the heat flux harmonics in Fourier space. So we need to go back to the real space using Fourier cosine transform in our case. And we can also estimate the temperature of the plate by solving the direct problem using the estimated heat flux. So we estimate the temperature harmonics and finally the temperature field during the droplet impact. Because with a metallic plate, we are measuring the back surface temperature, but I'm interested on the surface, on the impacted surface temperature. So that's what we are estimating with this equation. So here you can see the results. We have the shadow graph here, very nice images. This is the infrared thermography images. And this is what I showed you, the estimates from the heat inverse method, the heat flux evolution over time and the impacted surface temperature evolution over time. Okay. We just had a paper accepted validating this method. If someone are interested later, I can send the paper. But we can see we can have a quite detailed profile of the heat flux evolution and surface temperature during the droplet impact using these synchronized images. So as we have heat flux for the spray application, normally I'm interested in how much energy does the droplet dissipate when impacting the surface. So to do this, it suffices to, this is the result for 290 degrees. So I showed you here. And also for 460 degrees, a higher temperature, we can see the droplet rebound and now a different surface temperature, different heat flux profile here. Actually, for this case, as we don't have breakup and contact between the droplet and the surface, we have a more well-behaved profile, let's say, for the heat flux over time. But as I said, I'm interested on the amount of energy that's dissipated during the droplet impact. So we need to integrate the heat flux over time and space. And when you do this, we go from megawatts per square meter to joules or joules of energy. So these are results we have depending on the surface temperature, the droplet Weber number, and in two different representations of the same results. Because of the time, I'm going to concentrate more on the models where we use these results. But one interesting thing that happened, I presented preliminary results we had in a conference there in Edinburgh, hosted by the University of Edinburgh in 2023. And talking to Dr. Yutaka Kita, he had very different results compared to what I had. So we decided to investigate that together. And Carlos was an undergrad student here from the lab. He spent some time in King's College under the supervision of Dr. Kita. And after compiling a lot of data from the literature, there is a very big difference in the amount of energy reported in the literature. There are some results of microjoules of energy and others of joules of energy. And that's evidently because of the droplet sizes tests that they tested. If you test much larger droplets, it's going to dissipate much more energy, that's for sure. But also we compared that for very different droplet generation methods, from single droplet to droplet streams to spray cooling. So although working with 5 orders of magnitude can be tricky, so there are some studies that work with effectiveness, or what we prefer to call efficiency of droplet impaling cooling process. And the droplet heat transfer efficiency, we can say that the amount of energy the droplet dissipates normalized by how much energy could it dissipate, let's say if it was heated until saturation, and after if the droplet was completely evaporated. And when we do this for single droplet impact, for droplet stream or spray cooling, even for those very different droplet sizes, now all the efficiencies are falling inside the same order of magnitudes. So that was very nice to see the droplets collapsing very close together to the same order of magnitude. And that's reasonable because the droplet mass depends on the third power, the cube of the droplet diameter. So what we decided was, okay, what if we try to model the droplet efficiency to see if that works? And then we tried to do a scaling law model just to see how it was working with using scaling laws. So let's say the droplet impacts the wall at a given velocity and it has a size d at time 0. And during the contact time, it becomes a pancake with a diameter dc constant constant vapor thickness, and we have heat conduction during this problem. And then the droplets bounces off the surface. We have a scaling law, as I said, process. We are working the Leidenfrost regime. So the data we collected is only regards the Leidenfrost regime, at least as reported by the authors. And then we have the total dissipated energy as the integration of the heat flux over time and space. So if we consider heat conduction, we have heat conduction through the vapor layer, and then we have the vapor layer thickness here playing a role. And when we wanted to, as I said, scaling law. So let's not take the vapor thickness for an impacting droplet, but for a sessile droplet for a moment. And that's a quite well accepted model for the moment in the literature, as reported by Anne-Laure Biance and Guillaume Castagnet. And then we have this model here. Let's put that in the equation. And now we have a contact diameter and a contact time to model here. So we took our results and we saw that depends on the Weber to the 1/3 power. This exponent can change a little from the literature, but we have other authors that reported the same power as us. And we used Rayleigh oscillation time here as a characteristic time. And then when we put that, we have this equation for the amount of energy which is dissipated. So if we put that as an efficiency now, it suffices to divide that for the maximum energy it could dissipate. And if we take that for water at 1 bar, the sensible heat is about 14% of the latent heat. So if we take this and put them all together, this big equation becomes this very simple correlation here, where we now have the efficiency depends on the temperature difference and the droplet Weber number. We have a fluid parameter here, which we call sigma. For water, for example, we have this value. And now we have, as always, we need in a scale law, a fit parameter. And considering the data we collected, the fit parameter is 2.8. So we were happy to see this parameter because it's in the order of 1. So the scaling law we used is not too far from, let's say, reality. If we found, for example, a fit coefficient of 1,000, we saw that something was not right, but it's close to 1. So those are good. That's good news, actually. So what we did, let's compare that to other models from the literature. We have Mishima's, Lelongs and colleagues, Breitenbach and colleagues, where they had very elaborate models. And let's try to compare with the collected data. But this comparison, what we did, we used the parameter sigma 50 as a parameter. So this parameter is how much data, the amount of data in percentage that's estimated correctly by the model with an accuracy of 50% or better. That's kind of funny because 50% is a lot, we know. But when you compare the models, we're going to see 50%. If we are within 50%, it's very successful, actually. And now we are considering all the data we collected. In this case, we are talking about more than 1,000 points. And we also did the analysis considering removing Gradex data and colleagues' data from the analysis, because among the more than 1,000 points, more than about 900 points came from Gradex and colleagues' data. That's a very powerful database they have, and that's only possible because they did a transient analysis. So that allows you to have very good and very large database. So to be fair to the others, we also did this analysis removing their data and also comparing the data from our paper. And when you see this, Gu and Mishima's model performs quite poorly compared to the data. It underestimates a lot the cooling efficiency. Lelong's data performs very well using Gradex data, but with the others, it underestimates a little the results. When you take Breitenbach and colleagues' model, it captures well the order of magnitude of the cooling efficiency, but the trend, there is something missing. But it goes much better than the others for a moment. And finally, the ones that we fit, of course, we use the fit parameters here with the semi data. We know about this limitation, but it's capturing the trend quite well. And we have a good amount of data, well estimated within 50% of accuracy. So this has been very recently published here. So that's something that I was waiting to do this presentation, to have some kind of validation of what we are presenting. But what we are working now here in São Carlos is trying to improve this heat transfer model. Okay, now we need to consider the dynamics of droplet impact. What if it's not in the Leidenfrost regime? So we have other techniques we are implementing. We are quantifying, for example, the solid-liquid interface, droplet coalescence. When you don't have any more a dilute spray, let's say we have a denser spray, we are starting to study droplet coalescence and secondary droplet quantification as well, because that's going to help us with the mass and energy balance of the systems. So it's still a work in progress, but that's what I want to talk here. And then the main, I know I did 2 talks in one in industrial scale, one in laboratory scale, because there is still this large gap between the 2 of them. And it's very challenging when involving quenching. But the thing is, even for the same scale, for example, for a laboratory scale, as I showed you for droplet impact heat transfer, we need these pilot scale experiments, but even at laboratory scale, we still have a large discrepancy between the data and the results and the models. So we still need more research on that, even before, or even maybe together, there's a scale change in quenching and heat transfer. Because the idea here for our group today is that dripping droplets hollows out stone. The idea is that droplet by droplet, I'll have a spray someday. So maybe we need to start interacting the droplets, understand the dynamics and heat transfer involving interactions. And the concept of interactions can be tricky sometimes, but we need to investigate that to maybe goes from lab to industrial scale. So that's what I had to present here. I have to acknowledge the partners during my postdoctoral fellowship, Michel, David, Didier, Antoine, and also here from the ones that collaborated for this droplet impact experiment here, Carlos, Álvaro, João, and also Yutako. Thank you very much for the collaboration. I need to thank the funding agency, FAPESP, the University of São Paulo as well for the facilities and space. My research group, GOTAS, people here are being very helpful, working great, so I need to thank them. And for you all who take your time and patience to hear me, thank you very much, and I hope I can answer some questions. Thank you.
All right, wonderful. Thanks so much, Arthur, for the very nice talk. So now I think we have plenty of time for questions, which is great. So I'll ask the audience if anybody has any questions. Feel free to either raise your hand or just unmute yourself. Either one's fine. If not, I have one question we can kind of start things off on. I was a bit curious about your reconstruction model. I guess you have to assume some things about the contact resistance and things like that in order to kind of get it to work. If that's correct, do you have a sense of the kind of sensitivity these parameters may have on the reconstruction, and what should people pay attention to when they want to implement your technique into their setups?
Okay. Thank you, Matt. That's actually a common question when regarding this method. So let me see if I can go to this slide. I don't know if that's going to work. Yeah. So the idea is that actually you don't need to know the contact resistance nor your thermocouple response time in this method. The idea is that you have to do an experiment where you're going to simulate your instrumentation method. So let's say you just inserted the thermocouple in a large piece. So in this small piece experiment, you're going to insert the same way, you're going to tie it the same way, use the same material. And then you do an experiment using these 2 thermocouple sinus, for example. And then you're going to have, maybe I should go back to the other, I think the other slide was much better. And then you're going to have these 2 temperature data. And then what we do is that if you take the equation for the thermocouple response time that I showed here, I'm almost getting there, and you have a kind of a linear problem, right? So what we do here, you have the temperature measurements. So the TP, you're going to consider your ideal thermocouple as measuring. So that's the hypothesis. Your solder thermocouple, you're going to consider to be ideal. And then you have your slow thermocouple, which is going to do its measurement. So you have the temperature evolution, and then you have the temperature you're measuring with your thermocouple. So we use the least square method to estimate tau and Xi and the referential temperature. So actually, you do not need to know with your small scale experiment, you're going to estimate these values. And after you use the estimated values in your large scale experiment. So you have two strong hypotheses here. The fast thermocouple is ideal. So you can try to correct the ideal thermocouple as well, but that's one hypothesis. And the other one is that the contact resistance you have in the small scale experiment is the same as in the large scale experiment. So the parameters are the same. So that's what you do later in the large experimental setup. I don't know if I was clear.
Yeah, it makes perfect sense. So you have when you do the experiment, you have both of the measurements, and then that's able to help.
And the main advantage is that as you do not need to know the contact resistance you're estimating, so it's a very personalized, a very customized estimate for your experiment, your SpaceX.
Right. Great, thanks. Okay, yeah. Please go ahead.
Hi, Arthur. Good to see you, and thanks for highlighting our collaborative work. It's nice to see it's kind of presented in a very nice way. I had a question. Maybe we have discussed this over the collaboration, but could you explain a little bit about the infrared measurement? And obviously, you must have some like some coating on the backside to enhance the emissivity. Can you recall? Could you remind me what kind of coating did you use?
Actually, yeah, that's a very good question, Yutaka. Thank you. Nice to see you too. And actually, in fact, for the infrared measurement here, we paint the back surface as black with a black matte ink. Okay, that's actually one limitation that we are now studying, because we are now starting to measure the thickness of this ink that may or may not have an influence on the estimates. So the back surface is painted in black, so it enhances the signal for infrared camera. Okay. And actually, another important detail regarding our technique is that we do not know neither to know the emissivity of the black ink, because we use a thermocouple here. And at the same time, we are measuring with the infrared camera. We have an insulated thermocouple on the top. So it's a very thin plate. So we do a kind of relaxation test. So the top temperature and the bottom temperature are virtually the same. So we measure the temperature from the thermocouple and the signal from the camera at the same time. And after we fit Planck's law using the two data. And that's mainly possible because we paint the back surface temperature to avoid reflection from the ambient temperature, for example.
What about the transient conduction within the black paint? Did you consider it in the inverse method reconstruction?
The heat conduction within the ink, that's it?
Yeah, if that's like, if that's
yes.
thick enough to affect the temperature signal that you capture with the infrared camera. Is there any delay?
Yes, that's actually very good. Actually, for this work here, we didn't consider the thickness of the ink, so we neglect the heat conduction inside the ink. But that's something that now we are investigating the effect, how much is going to change. So we are measuring now, we are starting to measure. I just bought actually the thickness measurement measurer, and we need to do some simulations and calculations to understand the effect of the ink on the estimates. To be honest, I think that may have an effect that we need to consider, because the plate thickness we are using here is about 500 microns, 600 microns. So, and we can expect, if for example, we take the painter used in cars, they are about 100 microns. So it probably has an effect that we need to consider later.
Okay, thank you.
Thank you. just a complementation, that can be included in the method. You just have 2 layers in the heat conduction that can be implemented.
Yeah.
There.
Perfect.
Great. Any other questions from the audience?
I can ask you a question if I can. Hello?
Yeah, sure.
Yes, sure.
Hi, Arthur. Nice talk. So I
Thank
had a question on the dissipation plots that you showed. Okay, I don't know. I don't remember which slide that was.
This one?
So, yeah, this one. Is it? So I noticed that with increase in wall temperature, the dissipation is or energy dissipation is lower on the left. Is that true, or am I misinterpreting the reason?
Sorry, just to be sure, you're saying, for example, we are talking about this plot here in the right-hand side, right?
Oh, left one,
For
left
example,
one,
or
or the
left
right
one.
one. Actually, yeah, you have both. Yeah.
Okay.
Oh, this
Yeah,
is
it decreases
Mhm.
first, right? Yes, it decreases first with the increase in temperature, because here we are not in the Leidenfrost regime. It's okay. So we have contact here between the droplet and the wall. That can be seen, for example, here in the video. When I launch the video, you can see in the shadow graph images, we have a lot of atomization. And that's only possible because we have the bubble nucleation during the droplet impact. But here, for the other condition, a high temperature, we have droplet rebound. So the vapor layer thickness is already established. So yes, we can expect here to have this kind of minimum. And after we have this increase with the surface temperature, which is actually what we try to propose in the model. But regarding the model, for example, we are not regarding this part of the data, for example.
I see. Okay. And do you expect to see that? I mean, I was just curious because it was like a monotonic decrease, but wouldn't before you see the Leidenfrost effect, should it not increase a little bit? And then once the Leidenfrost effect takes place, then you have a decrease. Is that an expectation?
Okay, do you mean we should see an increase here?
Yeah,
and
right.
then a decrease, and after an increase, right?
Right. Yeah.
Yes, you are absolutely right. If we had some tests, we didn't put this in the paper because we tried to focus, to concentrate close to the Leidenfrost region and Leidenfrost region. But we have one of the students here, they did some tests at lower temperatures, and exactly as you're saying, it starts very low. Let's say we're talking about water here at ambient temperature. So when you have 150, 180 degrees, it starts to increase, then it reaches here. This is very close to the peak, okay? We have just a small increase here later. Then it decreases, then it increases again. You're absolutely right.
Okay, yeah. Thank you. Yeah.
Thank you, Suhas.
Great. Any other questions? Great.
Okay.
Hi, Arthur. Can I ask another question? Just to add to the previous discussion. So in terms of the dissipated heat for higher temperatures, there's one model that says like if you increase the surface superheat, yes, you have a larger temperature difference, but then you also have a thicker vapor layer. So they might cancel out, and maybe you might expect a pretty much constant heat dissipation. Do you have any comments on that or any observation like that?
Yeah, actually, also feel free to talk if you want to discuss the topic, because you also an expert in the field here. But that's something actually at a given moment, it's something that we still need more reliable data, in my opinion, for us to confirm some of these models. But in fact, you can have indeed this kind of let's say, threshold between the two conditions. But the thing is that the impact, the vapor layer thickness is also related to the droplet impact velocity as well. So I think that there is this kind of complex process involved in there. I confess I don't have today a very strong or based opinion on that. I never did some of the calculations to check on that. I don't know if you have already done some of these calculations, but we see most of the data, because one problem that we have in the spray cooling tests in general, that was something we saw there in the jet cooling process as well. If you can have some quenching at very high temperatures, even not respecting the thermodynamic limit of contact between the wall and the liquid, you know. So there is part of this data processing that can be kind of tricky to process. And I'm afraid sometimes that can mislead some part of the models. But it's something that, in fact, related, you know, because people usually talk about the radiation effect during droplet impact, but the heat conduction effect is much larger. Yeah. So it's a linear effect in one side, and the one side, and the almost linear effect on the other side. So it's possible that can compensate, you know. But I confess I don't have a very solid opinion today on this, and I think we need more data. I don't know if you have some comments on that. Feel free.
No, I thought that's something we can collaborate on.
Sure.
Yeah. All right, cool.
Thank you.
Cool. All right, well, if there are no other questions, actually, Arthur, I got a question not a question in the chat, but just a request. I think somebody messaged me directly, but it may pertain. What's the last paper that you mentioned at the end of your talk that you just recently published?
Yeah, this one about the droplet impact heat transfer. Here you can have the DOI. After, I think it's going to be available. The person can contact me. I can send the paper directly. But it was in applied thermoengineering, from single droplets to spray something model, experimental data model. But yeah, it was about 2 months ago, I guess.
Okay, great. Yeah, I just wanted to get that for them.
All right,
perfect. So yeah, thanks everybody for attending another TTC. Let's thank Arthur one more time for his great talk, and
thank you.
Wish everyone a good rest of your morning, afternoon, or evening.
All right, thank you very much.